Welcome to the Explainer. Right now, we are living through an absolute golden age of astronomy, and the discoveries we're making, they are literally taking the old textbooks and throwing them straight out the window. Have you ever pictured a planet shaped like a giant lemon, where it literally rains diamonds? Well, buckle up, because we actually found one.
Okay, let's dive into this absolute oddity. PSR J2322-2650b. It's this mind-bending exoplanet that completely, and I mean completely, defies every single model of planetary formation we have. When I first read about this, my jaw actually dropped. It's a world that, according to the physics we rely on today, just shouldn't exist.
I want you to picture a massive, Jupiter-sized planet. Now jam it so incredibly close to a dead star that the extreme gravity actually stretches the entire planet into this bizarre glowing lemon shape. So it's not a sphere at all. It is being violently tugged and distorted by unimaginable cosmic forces. Now, what's really interesting about this is the host star itself. It's a pulsar. That's an ultra-dense, rapidly spinning dead star that acts like a cosmic lighthouse, sweeping beams of radio waves through space. This creates an extreme environment completely unlike absolutely anything we've ever seen or even modeled in our own solar system. And the weather forecast here? Completely impossible. First off, you have an atmosphere of pure molecular carbon. No carbon dioxide, no methane, just pure carbon. Second, instead of water clouds, you've got these thick, dark clouds of soot drifting through an alien sky. And finally, the extreme pressure deep down inside the atmosphere actually condenses that falling soot right into diamonds. You would need a seriously reinforced umbrella because it literally rains diamonds inside this giant lemon. When Carnegie astronomer Peter Gao first saw the atmospheric data for this planet, his actual authentic reaction was simply, "What the heck is this?" And that is exactly what makes this so fascinating. Out of all the exoplanets we've ever studied, zero others have this kind of molecular carbon atmosphere. We cannot explain how it came to exist. And really, that's the whole theme of our explainer today. Because as our tools like the incredible James Webb Space Telescope get better and better, we are throwing those old rules away. We are in an era where the rules are changing daily, and our cosmic models are breaking down everywhere we look. Section 1. Breaking the universe's rules, the impossible early galaxies. Let's move to and see how this builds when we look at the James Webb Space Telescope's recent discoveries in the very early universe. We used to think early galaxies were like slow, isolated turtles. That was the old hierarchical model of slow galactic growth. But JWST found the exact opposite. Take a system known as JWST's quintet. This is a massive, compact merger of 5 giant galaxies happening just 800 million years after the Big Bang. And they are pumping out stars at a rapid rate of 250 times the mass of our sun every single year. They're already mature, they're pumping heavy elements into space when they really should just be starting out. So the crucial point is this impossible mass ratio of supermassive black holes to their host galaxies. In our local universe today, that ratio is about 1 to 1,000. But in these distant, early systems, like this little red dot known as Able 2744 QSO1, the ratio is a staggering 1 to 1. The central black hole is literally just as massive as the entire population of stars surrounding it. This 1-to-1 ratio is an absolute game changer because it proves that these supermassive black holes actually formed before the stars around them. It's massive evidence for the direct collapse black hole theory. Basically, instead of forming from dead stars, pristine gas clouds collapsed wholesale into massive seeds of 10,000 to 100,000 solar masses. And that perfectly solves the timeline problem of how these billion solar mass black holes got so huge so incredibly quickly after the Big Bang. Section 2. A background cosmic Hume. Nanograph's 15-year discovery. Now we're going to pivot to another massive breakthrough, where astronomers literally listened to the fabric of the universe itself. I want you to imagine space-time as a massive, vibrating cosmic dance floor. Those merging supermassive black holes we just talked about, they are out there orbiting each other in the cosmos. And as they do this orbital waltz, they rhythmically vibrate space-time, exactly like heavy dancers vibrating a wooden floor. To actually hear this vibration, scientists use something called a pulsar timing array. By measuring the incredibly precise flashes of 68 millisecond pulsars scattered all across the Milky Way, they essentially turned our entire galaxy into one giant, galaxy-sized antenna to detect ripples in space-time. And let me tell you, This was not a quick overnight discovery. It took 15 years of dedicated observation. It required a massive amount of observation time on the world's largest radio telescopes just to dig through the cosmic noise and finally hear this incredibly low-frequency cosmic rumble. It breaks down exactly like this. Supermassive black holes orbit each other, and that immense, violent motion physically stretches and squeezes spacetime. Over 13.8 billion years, the ripples from hundreds of thousands of these pairs overlap, and they create this constant, low-frequency background hum that we finally managed to detect today. Section 3. Asteroids and Life's Origins, the OSIRIS-REx Return. Let's bring the focus a little closer to home and explore how a long-lost salty asteroid is completely changing our understanding of biology. Back in 2023, the OSIRIS-REx spacecraft dropped off a sample of pristine rock from the asteroid Bennu. How much rock? Just 121.6 grams. That is barely a handful. Yet, it's the largest extraterrestrial sample ever delivered to Earth. It's tiny, sure, but because it was totally protected from Earth's contamination, what they found inside is fundamentally rewriting our perspective on life itself. And this brilliantly illustrates just how crazy the sample was. It was a chemical goldmine. It held exceptionally high levels of ammonia and formaldehyde, 14 of the 20 amino acids we use to make proteins, all 5 DNA and RNA nucleobases, and 11 ancient evaporite minerals. These are the literal, raw precursor ingredients for life, and they were actively cooking in an ancient warm saltwater brine before the Earth had even finished forming. So why does this matter to us? Because it means the chemical building blocks of life weren't uniquely forged here on Earth. They were likely widespread across the entire early solar system. Nature already had the conditions to cook up this cosmic broth out in the dark, massively increasing the odds that the ingredients for life could have been delivered to other planets and moons. Section 4. The climax. Rewriting the textbooks. When you step back and really look at all of this together, the diamond-raining lemon planets, the massive early galaxies, the cosmic hum, and this asteroid broth, a unified theme emerges. We are in the middle of a scientific revolution. Just look at the timeline of this current golden age. In 2021, JWST launches and instantly shatters our views of the early universe. Fast forward to 2023, we get the OSIRIS-REx asteroid data and the nanograph cosmic hum detection. In 2025, the Vera Rubin Observatory is set to see first light. And by 2026, the Roman Space Telescope begins an ultra-wide, high-definition all-sky survey. It is genuinely, absolutely awe-inspiring. With tools like the Vera Rubin Observatory coming online, we are about to watch a live time-lapse record of the entire visible southern sky, updated every 3 to 4 days. The pace of discovery is about to accelerate faster than anything we've ever experienced in human history. As Nikki Fox from NASA perfectly summarized, NASA's OSIRIS-REx mission already is rewriting the textbook on what we understand about the beginnings of our solar system. And honestly, that is true for every single source we explored today. We are entering an entirely new era of physics and astrophysics, where the old rules simply don't apply anymore. Which leaves us with one final, very provocative question to chew on. If our rules are already broken, and if our models of planets and galaxies are already being thrown out the window today, what impossible thing are we going to find tomorrow? Thank you so much for joining me on this explainer. Keep your eyes on the stars and stay curious.